I'm very pleased to be here tonight and this evening to present you, I will say, my perspective on the Metasurface. And so as Peter mentioned, I'm a lens designer, so working in optical engineering for a while, and I joined LavalUniversity in 2008 as a professor in physics and engineering physics and optics, with an industrial chair in lens design. And this chair brings company together in Canada to have at least one location in Canada to have training in lens design, and mostly also optical engineering, assembly testing, and for the last few years, we have also a fabrication lab where we have single point diamond turning, grinding, milling, and post polishing equipment to build optics, but optical component, but also freeform and things like that. So we are a pretty good situation in Canada for our industrial partners to provide support to them and to develop various things. So as a lens designer, so I've been involved in many areas over the last 20 years, and sometimes there is new trends in optics, and Metasurface is one of them. And when you will see also in my presentation that I will talk about also diffractive optics. When I did my master and my PhD in 90s, I did my master on stray light analysis from diffractive lens. And so I was involved in this diffractive structure, I will say, where at that time diffractive lens was something like new, and all people said, oh, it's going to be very interesting, we can do flat optics and we can have a lot of miniaturization, and it's going to be interesting for space and all things. And now with Metasurface and Metalens, we also hear about the same kind of things. And so from a lens design point of view, it's we know how to design diffractive lens, but one question maybe is how to design a Metasurface or a Metalens using lens design software. And there is a way to do it. And I've been involved during the last 3 years in what we call the Extreme DARPA program. We are the only one outside the US that participate to this program, actually, I think. And we have been invited by DARPA to participate exactly to do this, to have a perspective from a lens design standpoint about Metasurface. So I will present you today this how we saw this, and eventually discuss also a discussion about what's going to be the future and the perspective for this Metasurface. So let's start with the kind of very short outline here. So I will talk about what is a Metalens and what is Metasurface, and also what is the link with negative index material. And then one of the key things, I think, from a lens design standpoint is the difference between, if there is any, between Metasurface and diffractive optical element. So about the light propagation, but also aberration, dispersion, and various properties of those Metasurface, like tunability and things like that. And I will briefly talk about the fabrication process, but somehow you will see that the fabrication process is similar to diffractive lens to some level. And then we will jump to Metasurface in lens design, and I will talk about the work we did on the DARPA program. And some of those work have been presented in the SPI meeting and 2 years ago, something like that. And more recently, we did some work on what we call the retracing with phase discontinuities. So a way to deal with retracing through diffractive to Metasurfaces, which is, I think, the key for using it for a lens designer. So what kind of tools can be developed in Code 5 or ZMax to be able to ray trace to Metasurface. And so how we can model this. So I will briefly go to this. So what is a Metalens? So my preferred definition was this one from this paper, which talks about the advantage of Metalens over diffractive lens, which was published in Nature Communication a few years ago. And the definition is mostly that, okay, well, somehow a metasurface or a meta lens is a diffractive lens where the structure is smaller than the wavelength. So it means that if a meta lens is somehow a diffractive lens, not all the diffractive lens is a meta lens. And so the conventional diffractive lens, which is a CDL in the text here, is mostly I would just try to get my pointer. Okay, good. So the conventional diffractive lens, if it use a structure which is more or less larger than the wavelength, will not be considered as a metasurface. So what it means is really that the diffractive lens will use the diffraction to know where the light goes, and how the structure is built will have an impact on the efficiency of the lens. As opposed, if you look through the metasurface, it's a little bit different. And here I just have a cartoon that, okay, well, you have the standard lens, which is a standard positive lens, and you have a diffractive structure that is mostly driven by diffraction law. And the structure are micron scale level, so larger than the wavelength habitually. And then you have the metasurface, which is mostly structure that are sub-wavelength that are put on a surface. And somehow this structure has a quasi-periodic sheen that is repeated. So it can be seen as a diffractive lens, but the process to get the lens out of this metastructure is different. And here you have just an example of various type of metasurfaces. The first one is kind of a nano rectangular pillar, and the phase from those pillar are mostly the phase change is provided by the rotation of the pillar. So all the structure are the same height here, but the rotation of the structure will produce a phase modulation. And so you can have a structure that rotates and will produce 0 to 2 pi phase shift, or even more than that. And then you play with the structure to make a phase function. And as a diffractive lens, you have this phase wrapping stuff that you can use. But again, it's not come from the diffraction. It's come really for the rotation of the nanopillar. This structure is used what we call a geometric phase function. In B, you have a cylindrical structure. And again, those structure has the same height everywhere on the structure. The only difference is the diameter of those structure. So you can imagine, so what is changed here is the diameter. So the diameter of the structure will have an impact on the output phase. So for a certain diameter, the phase will be mostly a constant. And then if you change it a bit by so the phase will change, and then you can have a 2 pi change phase. And you can put those structure again to make a phase function, including this phase wrapping. And this nanostructure is more or less what we call a waveguide structure. And this word waveguide will come a little bit later also. And in C, you have another type of structure, which is mostly some very small disk. And again, the size of the disk will have an impact of the modulation. So this is 3 different type of structure. And of course, there is also some other structure, like what we call this, the structure with, all those structure are actually dielectric structure, but you can have structure also with metals. And the idea with metallic structure is you are able to manage the properties of the material to get some resonance at some level. And doing that, you can manage not only the phase, but you can change also how the light will behave to it. And this is what we call sometimes the negative index material. And here you have an output from Pachanberry paper early in 2000 about what we call how the light behaves to a negative structure. So you just give this cartoon in his paper and say, okay, if n equal -1, and you have a point source here and goes to a surface which has a negative index. So rather to have a refraction in a certain direction, you will have the refraction in the opposite direction, and then the light would converge in the center here, depending on the thickness, but this is what you will get. And then again, the light will go from this point, and again, when it goes out, it will be in the opposite direction. So this is why you will have this, again, this point source. So the image of the point source, or an image there. So this is what we call a negative index of refraction, and it can be any numbers. There is not only -1, it can be something else. And if you go to the mathematics of all this, you will see that all the aberration can be derived exactly as a standard lens, whatever the index is positive or negative. There is a thesis done in Arizona by, I just didn't remember the name of the guys, but there is a student there that have been working with, I think, with Joseph Sazian, and he has a thesis with negative index and derive all the aberration, and mostly shows that the aberrations stay the same. Mostly we'll have the same kind of aberration, rather than the index of refraction will be negative. And so, as I said, it's come from the Pendry paper about this, but negative index material have not been invented by Pendry. We make reference to Pendry, but Pendry also in this paper referred to a paper in the 60s from a Russian guys, which was Vassilako, probably well known by some of you guys. And so it was a Soviet physicist that derived a value, or a way that it says, okay, well, we can manage to have the permittivity or the permeability negative, and somehow this is the basis of how we can get a refractive index which is negative. So mostly Pendry said in this paper that n is the square of epsilon times mu, and habitual epsilon and mu are negative. And so if they are negative, as you do a square of this, you can handle at the end. You don't know if the index of refraction is positive or negative. So if you read the paper, it's very interesting for that. However, it's a kind of meta material somehow, because you can manage the light with very, very particular properties. But the problem is mostly you have to build something that plays with metals, because you need electrons to have some conduction at some level, and to make some resonance. And so it didn't make those materials very suitable for optical application, as you have a lot of absorption of the light. If you send light through this, you will imagine that the transmission will not be very, very, very good. So that's what we call the Boeing cube, but you can find a lot of those things. This had been developed for a gigahertz range, but now we are equipped to manage to do this in visible. So you can have some metallic structure into the material that give you some resonance, and then you can have very nice properties. But again, it's very hard to manufacture or to mass produce these things on a standard way. So it's still a lab curiosity, actually. Okay, so what's happened? Okay, good. Oh, okay. Is it this? Why? Okay, yeah. Okay, I just remember in 90s, I was working at National Optic Institute, and at that time we are building our coating based mostly on mud ice structure. So mainly some structure that can modulate the volume of material as function of the depth. And this structure habitually was smaller than the wavelength, and that's a way to do our coding. At that time, nobody told this metasurface, but it was clearly a metasurface. And actually, nano structure or spherical nanostructure can be used with deep coating to produce such higher coating, even in optometry. so in glasses industries, to do very cheap coating, RR coating based on that. So that's the first kind of I will say metasurface that I saw in when I did my master and my PhD in 90s. So if we look to how the light is propagated, so I was talking about those metal lens, those structure, when you rotate the nanopillar, it will change the phase. But the idea is somehow to compare with or to make some reference between the refraction. So we all know that the refraction coming from a lens, a Snell and things like that. So the diffractive lens is mostly governed by diffraction, and diffraction, we know the diffraction, and we know how to calculate the dispersion from this lens and things like diffractive lens can have multi-level. It's the same as you rather than working in the first order, you're working maybe in the 10th order. It helped to control the light dispersion somehow, so it's interesting. But the structure tend to be deeper, so you need to the structure to be very depth, but the period is longer, so at somehow it can be interesting. And as I said, the nanostructure, like the nano pillar, it's really then when you rotate the structure, and then you have on the right side you have a graph that shows that if you rotate the nanostructure, you will have a certain phase shift that coming out of that. There is a couple of line on this graph, not that important actually, but what you have is mostly in green and blue. You have what we call the Pachanberry phase function. So if the size of the structure is well, the proportion is well done with the index of refraction, you can have a perfect phase which is linear with the rotation, which is a Pachanberry phase. And the other things you can notice on this graph is this is polarization sensitive. I mean that the electrical field coming out of this structure will have a X and a Y component. So you will have a phase output in the X and the Y, and potentially if you put all those things together, you will have a phase gradient which is different in X and the Y. So this is the kind of structure, because of this birefringence behavior, you can use the structure to manage the polarization. And that's a properties of those structure that is not available in diffraction in diffractive lens. So that's something interesting if you want to manage this. And the solid lines come from LM means numerical, so is FDTD analysis. And the other line is come from our model. We tried to model this. I will come back later on this, which is not a very good figure. I will explain why there is some departure actually. But you clearly see that the rotation gives a phase shift. It's not the only structure. For this nano-cylindrical structure with the diameter of the cylinder, you can also have this phase shift. And this is very particular to those metasurface structure, that the behavior is not as a certain there's a certain shape or certain behavior according to what kind of structure. So the structure engineering of the structure shape will have an impact on how this curve looks like. And there is a lot of research actually going on all around the States, I mean, and all around the world, probably just to figure out what is the best structure for this. And I will show you a couple of examples of metasurface later, and you will see that the shape of the structure there is a lot of different shape available on the market. And somehow it's also a problem from a lens design standpoint. And so if we go through this different way to deal with the phase, and you see, okay, well, what's going to be the differentiator between the metasurface and the diffractive lens? I put a list of a few items that we can find in the literature, but mostly one of the advantage of the metasurface was, it was compatible with the CMOS processing and all this stuff. But again, the diffractive lens is also compatible with that, with the lithographic process and all these things. So it's not really a differentiator. Both exhibit chromatic correction. So the dispersion, with well known that the dispersion of a diffractive lens is it in the opposite way of standard refraction. So that's very cool to do achromatic correction, but you can do the same with the metasurface that's been demonstrated for a while. Somehow the metasurface can be used to have a very high index, high numerical aperture lens, so very fast lens. For the diffractive lens is somehow limited because of the shadowing effect. I mean that when the structure, because of the depth of the structure and the period, sometimes the light will hit the other structure, so you cannot have a very huge numerical aperture, which is not the case for a metasurface because the height of the pillar are always very small, and it's about 100 nanometer, or it's in the range of hundreds of nanometer rather than micron scale for a diffractive lens. Metasurface can be used for polarization selectivity, which is not the case for diffractive lens. Diffractive lens mostly will suffer from the polarization state, like the diffraction efficiency and things like that. And both can exhibit some tunability. I think the metasurface has a wider range. It had been demonstrated that you can tune the nanostructure, so change the phase quite efficiently with the meta lens, with the metasurface, rather than diffractive optical element is a little bit more complex, but you can, if you want to tune the diffractive lens, you have to mostly deform it to increase the grating period and things like that. So it can be done, but it's limited. So somehow there is a few differentiator actually, 4 of them that are of, I will say in the community that this is very interesting. There is some drawback. I will come back later on this. And so one of the things that the lens designer could be of interest is really the dispersion. And if you look more deeper in the dispersion, I just put some numbers and some information about, okay, yeah, we'll have this refraction lens that have a certain V number that can be calculated, but if you calculate this for a diffractive lens, you will get this kind of relation, which is very nice, which is mostly the wavelength difference of the waveband you want divided by what we call lambda d here is the d line, but at the same time that it is the wavelength that the diffraction structure is designed. So it could be what we call lambda 0. And you probably saw that for a diffractive lens, the focal length varies with lambda is equal to f0, the design focal length, times lambda divided by lambda 0. So that's exactly the same lambda 0, which is lambda d. If you design for a diffractive structure in the middle, for the middle of invisible. And yeah, so, oops. Okay. So to go with the meta lens, it's not as easy to derive the V number and how it behaves. And to have a better understanding how the light will behave into the structure, the way to do this on my side was really to dive into how the light goes into those nanostructure. And what we found mostly is based on work from a guy called Mercantili in 50s, I think, about the propagation of the light into a waveguide structure. And you remember at the beginning, I show you a couple of different type of metastructure, and I say, okay, well, this one is a guided structure. So it means that if you want to know the phase that's coming out from this nanostructure, you forget that this structure is small, and you just calculate what is the propagation mode inside the structure, and what's going to be the phase at the output. So it means that you compute the electrical field at the output of the nanostructure according to the rotation of the structure, but also according to the index of refraction of the substrate, the the material of the nanostructure, the dimension in X and Y, the height of the structure, and eventually the orientation, and potentially the incident angle on the structure, and also the polarization of the light coming in. And if you do so, you come with this output electrical field, which is a vectorial, and then you can extract from this the phase, and yes, the phase of this, just getting the argument of this and getting the phase. And then if you do this for one pillar and you do this for the other one and the other one and the other one, so you will have a phase gradient. And the phase gradient will give you how the light behaves and how the light goes. And again, you don't care about too much about the spacing between the structure, because you know the spacing is quite compact. So it's so you just calculate for each pillar what's going to be the phase output. And surprisingly, it works. It's worked pretty well. The only things that you don't know when you start is how many modes you need to propagate inside this very nano waveguide. But if you calculate enough modes, you get something which is quite precise if you compare with the FDTD analysis. And if you remember the graph I show you from the rotation, how the phase behave, you have what we call our model. So the model comes from this. And in that case, we have only one fundamental mode. But if you use another mode, the second mode and third mode that going through the structure, you get closer and closer to the FDTD analysis. And so that's it looked like a very complex equation, but yeah, is it complex? But it gives the opportunity to calculate everything. So if you get out this argument from this output, and again, because the structure is polarization sensitive, we have to get this for a certain X or Y position. And if you do so, the phase output can be computed and get an equation which look like more simple. What you have to understand mostly is here you have the theta, which is the rotation, theta n, which is the rotation of the nanostructure, and theta high here is the incident angle. So if the angle is 0, if you have a normal incidence, this equation become less complex, I will say. So again, you have this graph that shows that the difference between this, let's say this solid line and this dashed line is quite smaller than the Pachanberry approximation. Pachanberry approximation is the one that could be used habitually to say, okay, well, I want to design this phase function. So I calculate with Pachanberry what's going to be the rotation of the nanostructure, and then that's the structure I will build. But like you can see here, it's not exact. Pachanberry is not always good. Pachanberry is good for a very particular type of nanofins, particular dimension of the nanostructure in that case. So if you tune the properties of like the width, the height, and the index of refraction of the nanostructure, all the curve will become the Pachanberry one. So you can have a perfect fit if you want. So if you have now, if we will look to this, but at different wavelength, because we are talking about the output phase, but how the output phase varies with the wavelength, because we were interested by the dispersion. So we come out with this this kind of code. Now the structure is not anymore the rectangular structure. It's the cylindrical one. This is why we're talking about the radius here. And why we use the cylindrical one is because the cylinder are insensitive to polarization, which is something very interesting for a lens design, from a lens design standpoint, because if we design a complex lens and we use metasurface, we don't want to have interference by polarization. So what we have here is the green one. The green curve was what we call the design wavelength. But if you look to this curve with different at 500 nanometer and at 562 nanometer, you can see that we have, of course, a different scale. But what is interesting is that the difference between those two curves are not exactly constant. Relatively, from this side, you will see on this side, it's not exactly the same percentage in shift between the green and the blue one, for example. So what's happened when we reconstruct the phase, is the right graph here. You have this little change bump here. So what it means only that it's not like a diffractive lens. A diffractive lens, when you change the wavelength, is mostly, at least in the sign on the angle, so you have mostly a linear shift. So the focal length, linear shift, and all this stuff. But with the metastructure is a little bit different. So it makes the dispersion control a little bit more spatial. But this is very small change. So if we compare, we put this in Zmax, for example, and we compare with the lens where we put the diffractive structure using binary optic 2. And here, the exercise-wise, just to see the transverse aberration for a certain case. And so we try to reproduce the same kind of dispersion in both sides. And what you can notice here is those little bump here in the dispersion for some wavelength. And it comes directly from this little change in the phase according to the wavelength when you go and you move across the diffractive structure or across the metasurface. So it's even if the curve looks similar, it's not exactly the same. So at some level, for very limited F number, I would say large F number or very low system, the diffractive structure, at least in the far field, will behave mostly exactly as a diffractive structure. But if you go with a smaller F number, you begin to have a dispersion which is can be quite different. And somehow this is also properties that can be used, and it's going to be one of my conclusion of this is dispersion engineering is one of the key factors probably for the future of metasurface. So I said that I will say a couple of words about the fabrication, and so mostly it's diffractive structure rather than it's very small, so it's difficult to have a lithographic process like a standard lithographic process with this kind of structure. So it needs to be done with mostly e-beam lithography or of FIB, focus ion beam, like etching or something like that. And somehow it's just that if you're not familiar with e-beam lithography, what it means that you use an e-beam to do the lithography, and an e-beam is not very, it's not like a UV lamp that you open and you expose the photoresist to a mask. You have to scan all the surface. And so it means that it's a very long process. So the idea is to build a lot of lens on a wafer, like in CMOS industry, and then you have something that you can easily, you can have a cost-effective solution. But if you want to do a prototype, so e-beam can be used, but it's a long process. So this is why most of the time proof of concept of those metasurface of meta lens are done on very small scale because of this constraint to some level. So so on my side, I have a focus ion beam from an electronic microscope that I can use to build nanostructure, but we're not specialized in building nanostructure. We rely on some other very good, nice place that have experience to this. There is some way also to have a lithographic process, which is it can be a rolling process for eventually mass production, or imprint some structure, some very small structure on thin films. So this is something promising, like they already did for diffractive structure. So that's something interesting. So now let's just jump to the metasurface and lens design. And there is a lot of example in the literature about the design of a lens, that, an achromatic lens, or and this is an example here of very bright people from Harvard and MIT, I think, that they built what we call, you know, a very wide angle lenses, mostly diffraction emitted fisheye lens. And they use, remember that I said that the structure that you use to build this, the phase function from the lens is different from one lab to the other. So you have the structure here, which look like some very special shape, and also this is H shape, and there is a kind of little line here. And so this is what they use to control the phase. So somehow if you have a phase, you can have many ways to drive this phase. So they use actually this technique. This thing is mostly has been built with this kind of dimension. That it's a very simple system. You have mostly an aperture stop of 1 millimeter in front of calcium fluoride glass, and then you have some light that enters into the system, and you have a kind of telecentric field lens that is used just to image and to get a point, or an image of a point here. So I don't enter into the detail. I think that the people who build this are probably better than me, but from the paper, what I found is, so the structure is optimized that they have a phase for the central field, and they add a phase function for all these fields, and they put all these phase together to have a perfect or a phase that will match everything. And so at the end, you can see that for various fields, the image quality, of course, you can see some artifact or whatever, but it was just unfortunate that actually we do not have a full image. Okay, it's only very limited image at various, if you see the setup here is only that the light coming at one angle that gives a very small cartoon here or image, but not a direct sensor there. But you can easily imagine that one of the problem when you see this is really that you have all this very fancy stray light or structure or scattering or whatever you call it around that. So if you have a perfect large image of plus or minus 82 degrees, you can imagine that the image will be quite blurry, and like a diffractive, like it has been done in 90s with diffractive lens. The first diffractive lens, there is a lot of higher order stray light that going through this and make a kind of very bad contrast. But this is very nice development, and there is a lot of example. But I point out something here that you can see that there is only one structure here. There's not combined with a refraction lens, or it's not combined with many lenses. It's it's only one lens. So you have a collimated light going through this. So you know exactly that's going to be a collimated wavefront. And then you have to calculate the phase needed to focus this wavefront. So you can do it by hand, okay? But if you imagine that we put other lenses in front of this, and you try to optimize the structure as well as the other lenses together, now you don't know the exact wavefront that's coming on this surface. So you cannot calculate the phase function. And from a lens design point of view, it means that if I want to design, let's say, a triplets that use a metasurface, I need a way to optimize the metasurface as well, or during the same process that I optimize the other lenses. And or it can be more complex than the triplets. But anyway, what it means that it's the metasurface is maybe not the first surface of the design, and it's maybe not the last one. If it's the last one, as you have example here, you can get the phase just before the structure, and you know the phase output from this, and then you can calculate the phase you need. And the same for if you put it on the front surface, you know that the light is coming from the infinity, for example, so you know you have a plane wave. So when you know which wavefront is incident on the structure, and you know what you want at the output, you can calculate the phase. But if you are in the design process, you don't know exactly what's going to be the phase that's coming in the structure. So, and the idea with that we have in my lab is just to try to understand if we can build a model of those lenses and put it in the lens design software to optimize it, as we optimize any other type of lenses, or as we optimize the phase function of the diffractive lens. And so the idea is it's in an extreme case here, but let's say that we want to put a diffractive lens at this position on the lens on the lens number 6. So how I can do this, I don't know when I will optimize what's going to be the wavefront that's coming in here and what's going to be the wavefront going out. And the other things I don't know because of the pupil shift. I don't know exactly where the chief ray will goes on the surface. So again, it makes difficult for me to optimize the phase of the metastructure by hand. So I need somehow to use the lens design software to optimize the metastructure as well as optimize all the other lens in the complex optical system. And so what I said here is mostly that when the light comes, especially with off-axis, the lens will not behave exactly as a diffractive structure. It's a kind of is the same things as the dispersion, which is not like a diffractive lens. So if we go with an angle, it's going to be a little bit different than a diffractive structure. So if you use like a phase function like binary optic two surface, you will optimize the phase of this and you can translate this to a diffractive lens. It's going to work. But if you try to transfer it to a metasurface, it will work until the angle is limited. But if the incident angle of the rays change, the behavior of the structure will not be predicted well by the binary optic to surface. So somehow we need a model, because without a good model that we can use in the lens design software, we will have to use an FDTD code, and this is a very long process and computationally intensive, and it's going to be too long for a lens designer to wait for the FDTD analysis. You can imagine that you run I'll say 1,000 iteration of optimization, and then each time you have to do a FDTD analysis that took an hour. That's no way that the lens designer will use a diffractive surface, a metasurface in that case. So as I said before, our approach was to find, okay, well, can we have a simplified analytical model for that? And I already show you some result of this. This is based on the fact that yes, if it's a structure that is driven by waveguide structure, we can calculate the phase from a waveguide. And if we calculate the phase from the waveguide and we have many waveguides together, we can calculate the gradient of the phase. And then when the ray will come at this position, we know exactly how the ray will deviate because of this phase gradient. And so that's why we built a DLL and ZMax to do exactly this. So this is just a quick example of all this, but we mostly add at the end in ZMax. We can optimize the dimension, the length of the rod, the width of the rod, the head of the rod, and the material. Potentially we can change it to anything. And then we have a DLL that can optimize within a design like other type of lenses with a DLL and use the standard optimization process. We can do this also in Code 5, and it works. It works pretty well, in fact. But it's not perfect, but it works. And so here you have a couple of comparisons from the phase we get from ZMax according to MATLAB. So you have the kind of process, and also we have compute some OPD coming out from the surface, from the nanostructure dimension, and then we can eventually calculate the aberration produced by those surface, and then eventually compare to diffractive lens or standard lenses. And at the end, we can compare also with binary optic 2 with the diffractive lens and see the difference. And here you see the difference in aberration produced by, as I said before, when you come with an angle which is not normal incidence angle, it become to be very different than a diffractive lens. So the idea to use the phase function, only a phase function which is based on diffractive structure like binary optic 2 and Zmax is not the best way to deal with a diffractive with a metasurface, and those graphs shows that it's different. And see, this is a couple of example of design we did, like what we call a meta-cook triplets. Of course, I don't think that we need a diffractive lens or a metasurface to design a Cook triplet, as long as the Cook triplet already correct for all the total aberration. But it was a kind of academic exercise, I will say, to just demonstrate that we can put a metasurface somewhere in the design and get the result, which is quite similar to what we get from a refractive one. And what is important now is to know that, okay, well, if we do that, and we come out with the metasurface phase function, though if does this phase function can be manufactured. And this is the example here you have. It's a kind of flow cycle of the design. So you have this flow chart here with the retracing, and you have this DLL, which is the DLL composed of a few things. And then at the end of the optimization, you have the spot size you want, or the aberration you want. And then you can extract the phase function of your metasurface, and then you can use there's many software on the market that can build your phase according to some structure. And so you have a kind of element drawing of your metasurface, and those software will give you the output phase, and then you can get back this output phase into the design and see if there is difference between what you have calculated and what you can build. Because at the end, if you want to build the things, you need something which is feasible. So that's a kind of process that we put together actually to build a lens. I discuss also about this behavior with the incidence angle, and we also study a lot of these nano-cylindrical structure because they are, as I said before, polarization insensitive. And so we compare our model with the various FDTD analysis, and as you can see, our model fit quite well. And the model is mostly based on the modes that are propagated to the nanostructure. And again, we calculate for each of the output of the waveguide just the phase, and the phase will give us a gradient. And this is the only things we use. And some of you will say, well, but what do you do with the airspace between the structure? And again, the structure are so close to each other at some level that the light goes through this will not see, will behave exactly as I said with the waveguide phase output. And we are very surprised that it fits pretty well, but it seems that is the case. Now, if we go with some incident angle, which is not zero, normal incidence, the things are a bit weird, and we are still trying to understand what's going on. But our first model, as you can see here, the model is invariant of the incident angle for this structure actually. And this is mostly because of the propagation, the mode propagation. So here you can see that for a cylindrical structure, there's a couple of modes according to diameter of the phase you want to have. There's many modes that can propagate. And if you add modes to the structure, now you can fit this an incident angle of 15 degrees or 25 degrees. So you just have to increase the number of modes inside the structure when you come with a different angle. It's still very early stage work here, but it looks like it's feasible to predict how it behaves. And of course we analyze a lot of like the dispersion behavior. We didn't normalize everything here. You have a constant phase shift at 0 for the radius of 40 nanometer, but mostly, it's a constant phase shift. It doesn't matter, but it gives us a better view of the difference between all the curves. And you have our model and another software called PlanoSim results, so we can compare that the model is not that bad. So we just compute somehow some change in the phase according to the wavelength and so the dispersion of this. So we try to figure out what can be done on the dispersion side, because if the model can be good at normal incidence with a certain wavelength, but we need the model to be good at various angle of incidence, but also at various wavelengths. And here we can also play with the phase, what we call a phase map, according to two properties, mostly the rotation of the nanofins and the angle of incidence. And what is interesting actually with this is, this is the phase for the model, but and the idea behind that is if we have a map like this, can we use a kind of lookup table to determine the phase of the output? So here the color is the phase, the output phase is in degree, so 0 to 2 pi, according to the combination of an incident angle and a rotation. This is for the rectangular nanostructure. We can also do this for small angle, meaning that if we convert the equation with theta, which is equal to sin theta, and cos theta equal 1, we can also compute the phase function. And we just run through this to the third order and eventually to the fifth order and see what is the difference between all this. But again, the idea is, rather than computing this huge equation and get the phase out of this, if you have a map like this, maybe we can have a lookup table. And the idea behind that is, remember that I show you that the nanostructure it can be different from one lab to the other. Okay, they prefer to use this kind of structure, and this other one prefer to use another structure. So it means that from a lens design standpoint, what I need in my software is a structure or is a phase map like this that give me the already compute all the situation possible from this vendor, like test plates. You know, if I use if I use the shop from Metalens company, I will use this table, and so I will use this lookup table. But if I want to use a lab in Australia, nanophotonics, I will use this phase function. So somehow getting out a kind of lookup table approach is something interesting. So we did some work to this and to find how many points from the phase function we need to get the good results, and it works. So we can have we can have a model which is a pretty limited number of points and still have a good behavior of the surface. But again, it depends the quality or the precision you want at the end. So so what's going to be the future? You know, there is not a lot of companies out there that are selling Metasurface. Actually, there is companies that are building diffractive lens that now claim that they do Metasurface, because that's, the first definition I've give you at the beginning says the diffractive lens, if the structure is as small as possible, is comparable to the wavelength, you can say that's the Metasurface. Though there is American marketing stuff here that company are doing Metasurface, but that they are doing mainly diffractive optics. But there is one company actually in the States that is called Metalens, which lens with a Z at the end. So and they claim that they will be in mass production soon, and so they will produce structure that will be based on Metasurface that will probably be used, and that's the second point here, to replace the diffractive optical element, like for 3D time of flight module on your cell phone, for example. Those modules use diffractive lens, both lens and grating, to distribute all those points in the field that you can map in 3D your face or whatever you have. And they want to generate 30,000 point or 60,000 point. So habitually it's a Vessel matrix of a few thousand units, and then goes through a diffractive structure that will reproduce all this for a large number. It's less than actually for imaging. It's still not demonstrate that you can get a very good image from those structures. So nobody shows the stray light produced or as managed to show how to measure and compare the contrast, or state that, oh, those structure produce stray light and it's not as good as a standard lens for imaging. So we're still not there yet. There is a dream to have a flat optic, so a gain for TTL, so the total track length or weight is not clear from now. Of course, conceptually it works, but as I said, it's good to work, but at the same time, you have to get to have a good MTF at the end. Of course, you have to deal with electromagnetic field, so there's no simple way to get through this in a lens design software. And the idea to have this in the lens design software is really to democratize and give the opportunity to the lens designer to consider eventually metasurface in their design. And so we work on that, but still is not something that is all proof and works perfectly. So what we call real lens design tools still missing. Some like a test plate, as there's many vendor. And lastly, is the efficiency. I didn't talk about the efficiency of metasurface right now until now, but now I will discuss briefly about that. And so we know that from diffractive lens is mostly that if you are able to have a continuous structure, the efficiency is mostly 100%. And if you have a 16 level, it's 96%. And if you have a 4-level structure, it's going to be 81% or whatever. So I don't remember exactly the numbers, but this is the kind of number you can have with the diffractive lens. So and here during the last few years, you have this multi-level diffractive lens that exhibit something around 90%. Still for meta lens, you still see outside very low numbers like 45%, 40%, 50%. Of course, you can get very nice 92%, but nobody knows actually where the 8% goes, and it could be a potentially something which is very bad for imaging. So this is why on the imaging side, it's not clear how this will behave. For diffractive lens, it's very easy. You can compute where the light goes. It goes to the order 0 or the another order, so you can compute this and know exactly how the light goes and eventually see if it's bad or not. I just show you here a small list, but if you go to the Optica on June 19 one, I didn't put the title of the talk of this paper, but there is a list of something like they study something like 50 different paper with 50 different metal lens structure, and so they have a pretty good list of what kind of efficiency you have. And I just get to the end with some most recent things, and so very nice paper actually from Janik Roland in Rochester, and also with some other folks of I don't remember exactly where, but they use a fab lab from Minnesota, I think. But anyway, about meta optics, what you call metaform optics. So it means that this is a mix between the freeform and metasurface. And so they mostly demonstrate that they can write from E-beam a structure, so the metasurface structure on a freeform surface. So again, it's a very small structure that is built on a very small freeform surface, but it means that, okay, that's something feasible. So that's the kind of research that's going on actually to bring those metasurface to see how far we can go with the metasurface. The people from MIT, I think, already demonstrate that we can have a metastructure on a spherical surface, and probably they have some tolerance that the surface is not spherical but the freeform one. But that's something that new or recent development in the field. There is also a lot of not lens design, but software. The one is called Mirage, is from Sandia National Lab, and they have a very nice software that you can build your own structure, your own metastructure. This is very complex because it could be 3D structure. So on the side of software, it's very nice. And one of the software, it was published in Optic Express, I think 18 months ago. It's called Meta-Optics. I think it's Meta-Optics software. So it's a free software to design metastructure or lenses from a common code. So in conclusion, Metasurface and Metalens are very similar to diffractive optical element, but there is some differences in how the light goes into the structure if the incidence angle is not 0, and particularly for the dispersion. And I think, and I discussed this also with David Schaefer for a while, and which is involved also in the DARPA program, Extreme, about these metasurfaces that can control the dispersion to a very not as a diffractive structure, very differently. And then this kind of dispersion, if you have a very high dispersion, you can come with maybe some very interesting compact application, like a very compact spectrograph for cell phones, or something embedded into very small factor, which has a very huge dispersion to have a very high resolution or high spectral resolution and things like that. And I think that's maybe a way to deal in the future with metasurface. And we will have to wait again maybe a few years to see those metasurfaces with better efficiency or better dispersion control. And I know that one of the research that's going on actually is, as the structure can be shaped as you want, so then the nanostructure, people can find a way to build the structure to be achromatic. So it means that you can have probably in the future a metasurface which is by definition achromatic, without having to deal with the dispersion or combine with other negative dispersion or whatever. So the metasurface alone will be, and if you can get an efficiency more than 90%, I think that you can do something very interesting for that, if you can control where the straight light goes. So thank you very much for your time. I hope that I was not too long. And I will be happy to answer some question. Thank you.
Thanks, Thibault. That was terrific, really interesting. Of course, I still have lots of questions. I could start with a sort of a simple question and ask you if I'm thinking about it in the right way. Let's say we have that simplest metasurface with the cylindrical columns, right? And I think of each one of those as being like a pixel, you know? Mm-hmm. And so let's just say I had a piece that had an array of those things and they were all the same. So there's no gradient, and incidence angle is 0. They have a certain height, and so there's an optical path difference that you get from the height of the column. I'm thinking about this in a very simplified way. If the diameter of the column was very tiny, wouldn't that reduce to just the basic underlying surface in terms of the phase of the light as it goes through? And then as the diameter approaches the entire area of the pixel, doesn't the OPD approach that plus the height of the column? Does that make sense to you?
No, yeah, it makes sense. Yeah, that's this is why there is two things. The first one is the waveguide structure, and the phase shift occurs to a certain radius of those cylindrical. If the cylinder goes lower than a certain values, mm-hmm. there's no guiding anymore. So it's you cannot compute how it behaves exactly. I don't know. It's a kind of I may have to think about it. But and the same things, if you go too large, somehow you will fill all the space with glasses. And so you will have just
Yeah,
teeny
yeah.
holes of air.
Right, yeah,
So, yeah.
sure.
So this is,
So
yeah.
wouldn't it be a continuous function as you go from one limit to the other? Maybe not linear, but
Maybe not linear, but yeah, you have probably
that,
like some regime of operation which is
right.
different.
And that limit set by the height of the column and its index
Yeah,
would probably represent the the largest optical phase that you could change.
yeah, and somehow even if you increase the size of the cylinder, because I didn't discuss about this, but we check the there is the guiding mode get outside the structure somehow, and then if you have a structure which is close enough, you will have coupling between structure.
Mm-hmm.
So in that case, if the structure get large enough that the other one are so close that you have coupling between those structure, you may have some very weird effect somehow. And at the extreme case, is going to be like just, as I said, just a constant phase function.
Yeah. Okay, cool. And now one more simple question, then I'll let other people ask theirs. If you have a meta surface, in what sense could it be and have a negative index? Who cares about the index if it's all on a surface? Or does that argument about negative index only apply to a bulk meta lens?
To generate negative index, you will have probably to include some metallic structure.
Yeah.
Into your metasurface, and then the behavior could be very different. You deal with the electromagnetic field here, and I didn't discuss about that too much, but you can see those if you look how the light behaves, or all the electrical field behaves when it goes to the glass and to the air, is mostly that in the glass, the field will move the electrons, but not in the air. And so it's a little bit weird how you can try to understand what's happened at those level. And if you want to generate some impact on the you may want to add some metallic structure. You can coat with metal the side walls of those cylinder, and you will have a completely different behavior. And actually, people try to do this, to build a 3D structure that the walls has some metallic shape on it. It can be V, it can be C, it can be some structure, just some metal structure that will change the way that the electron moves into the structure. And this will impact how the light goes through this. And and those are very difficult to predict and to simulate, I will say.
Yeah.
In our case, we're with the waveguide is very simple. The theory are all there. It's just very strange that even at those small scales that this theory works. But
I need
works.
something very simple to support a mental model.
Yeah, yeah.
David Lee's asked a question on chat. He says, "Are you doing fabrication at Laval or just theoretical work? Are you having parts made outside?"
Mostly we use part made outside. We are in the process actually to fabricate an infrared lens objective. But in that case, the structure, it's for 3 to 5 micron waveband. So the structure is large enough that we can use our lithographic process. We will etch chalcogenide glass. And but again, the structure is smaller than the wavelength, but at the same time is large enough to use our standard lithographic process. And as I said before, we have this fucking ion beam system that we can use on our microscope. We didn't use it yet to build the structure, but we could. But there is many fabs outside that can be very helpful for this, and they are very good, better than us to do this actually.
Okay, I have another question. Penguin asks, "How do you see inverse design for metasurface design?"
I'm not sure I just want to be sure about what we call inverse.
I can't help you. Penguin, if you want to speak up, you could unmute yourself and talk.
Hi, yeah,
Hi.
hi, Professor. Thank you for your talk. Yeah, I saw some papers they are trying to apply inverse design that they can produce some very bizarre structures. So, because usually we build a library of nanostructures and we pick the structures. So it seems that inverse design can accelerate this design process, or
it's yeah, okay, yeah, well, I understand exactly what you mean. Yeah, it's you know, inverse design as you describe is, I think it's going to be hard to include it in the kind of process. But what I saw actually, if we are able to get a phase from our optimization, we could get a phase, and then we can try to find the best structure that will give this exact phase function, and a structure that can be built also with the exact dispersion we want and with the exact phase function output. And in that case, I think that there is software and there is group that are working on how to find the best structure from a structure library. And like as I said, if I want this dispersion with this phase output, maybe they could find the best structure to be built to have this wonderful metasurface or the exact metasurface we want. Because if we are limited with some structure, it may end up at the end that we are not able to get the right dispersion we want. So we will have to maybe refine the design because it will not behave exactly. And this is the kind of loop process I showed, that we have to get back once we have the structure or the drawing of the structure, we have to compute the phase from the structure and then going back into the software to see if it's work or not.
Okay, the questions are piling up here now. Greg Belanek asks, how sensitive are metasurfaces to the size or rotation of the features? Our manufacturing tolerance is very tight. Yeah,
that's a very good question. We start putting tolerance on this. It's not clear actually because I'm not deeply involved in the fabrication process, and it's hard to find people that will give me the exact tolerances of those things. It seems that it's changed from structures to structure. But what come up recently is, you know, all those shapes that are, you know, with very straight walls and straight angle are not as good as structure that are rounded. So I think that what's happened is there is structure that are less sensitive than other, or less, it gives more flexibility in the fabrication process. But definitely that's something that we have to be aware and take care in sometimes.
Okay, great, thank you. David Lees asks, are you working in only metal or structures that have both metal and dielectric in the sub-wavelength structures?
On our side, we're just dealing with the dielectric for the moment.
Just dielectric for the moment.
Yeah, we want to, because I will say from my personal perspective, I mean, that's maybe the only way to get very high efficiency structure. So this is why we concentrate on that for now.
Yeah, feels that way. Amy Stevens says, I feel like there are hidden restrictions on the nanostructure material. These do not behave like quantum dots, for example. No spectral absorption electronic states anywhere near the wavelength of the light. They just supply a field, in quotes. Can you comment or add or correct me? I think David's question is similar. Okay.
That's right. It's there is some resonance inside the structure, and I didn't discuss about it. But what we found, like on the cylindrical one, if we have to take care of a simple effect, which is the Fabry-Perot effect, and if we do that, and it will affect the output of the electrical field output and then the phase of this. So there is some resonance at some level, it's not like quantum dots, but it's something which is somehow similar. So this is why when you look in the literature, you will see some paper that talking about the resonance. And it's not only when you have metallic structure, but sometimes there's, you have some light or some wavelength that are mostly trapped into the structure. And you got some resonance and some, I would say, absorption of this particle light. But again, the only thing we study actually is the Fabry-Perot effects that has to be considered if you want to model correctly what's happened into this waveguide structure.
Mm-hmm. Okay.
I hope
Penguin,
it answers a bit the question.
Is that okay for you, Amy? Great. Penguin had another question, Penguin. For achromatic metasurface, for example, just 2 wavelengths, does that mean the nanopillars provide the same phase shift for the 2 wavelengths? And he says, go on, he says also, how would be the physical intuition behind that? A structure which gives the same phase shift for 2 wavelengths. Is it because the different orders of modes are being excited?
I actually for like if you for the nanopillars and things like that, if you want to have an achromatic correction, you will have to put 2 surfaces and manage the dispersion of one and the other.
Right.
There is a single nano structure like pillar stuff. There is no way that you will get the exact at 2 wavelength the exact phase shift. So it looks like it's going to be a phase shift which is different. But again, as I said, there's structure and there's research group that are working on structure that seems to be achromatic. So and I don't know yet the physics behind that and how it's solved, but that's the people that are working only on structure. So rather than having a nanopillar, they have a kind of I don't know, potato shape or whatever, and it works. So I'm not specialist on that, but it seems that there's some group that can handle this kind of things and try to find the best structure for visible. And so if it can be done, it's going to be interesting because you will have one surface which is mostly achromatic without any other consideration.
Simon, it may be too early for me to ask you this question, but I just wonder, do you have an opinion or a feel for where these are going to find an application first? What sorts of problems metal lenses will solve?
I think that one of the first application will be probably a monochromatic problem, and and I think that, as I said in the conclusion, the replacement of this 3D time of flight, you know, this point that are sent in the near infrared from your cell phones. It's a monochromatic, this laser shape, it's the laser stuff. So mostly this is very good for metasurface. But again, it's going to be very like, is it a diffractive or is it a meta lens, or, you know, it's a kind of, you play on the word here. But that's probably something that will have impact. And we'll have the first application, I think. Good. And it's probably 1 or 2 years from now that you will, you know, I think that the first phone vendors that will come out and say, oh, I put a metasurface inside my cell phone. I can certainly see that that's going to be a kind of marketing stuff rather than a truly metasurface, because if you look at with the microscope, you will see that the structure are not so small, but it will, the cell phone vendor will say, no, it's a metasurface. We're the first one on the earth that putting metasurface, and it's going to be a marketing. It's like it's like this year they says that they use freeform optics in the cell phones. I think that Xiaomi and Huawei claim this, or I don't remember which company, but there is at least 2 or 3 cell phones on the market that claim that they use freeform.
Okay, well, they would have to establish that the efficiency is essentially unity across the waveband. That I think would be a big challenge.
But again, if you are monochromatic, it's probably possible to
but cell phones
and it's not an imaging function. The resolution is large enough that it's not. It's probably possible.
Right. So for, yeah, maybe there's a monochromatic application. Yeah.
Mm.
Great.
Good. Thanks.
Yes. Anybody else? No. Thibault, thank you very much. That was really interesting. It's a subject that hasn't been talked about by optical designers nearly enough. I'm looking forward to hearing more papers at the IODC. I know there's quite a few.
Yeah, there's a few.
Yeah. So that'll be interesting.
We have
Really
we have a
appreciate
joint
that
session with the flat optics that will have a few
flat
papers.
plus, yeah, flat optics for those who don't know implies metasurfaces and meta lenses. That's what they call themselves.
Mhm.
Although I have lots of flat optics around my house, but windows and mirrors, you know.
Yeah.
But they call this stuff flat optics. Anyway, it'll be great. Thank you so much again, Thibault. It was really nice to hear from you today, and good luck
Thank
with
you.
this stuff.
Thank you, and